This is the second lesson of Advanced Functions Unit 2 about polynomial functions, and this lesson will discuss what some of the major characteristics of those functions are and some of the patterns that we notice, and some of the language that we're going to use to describe polynomials. So let's start with this concept here, that a function might be said to be increasing or decreasing on an interval if the graph is rising or falling. Now, this is not a bad definition here, but an even better definition would be something like an interval in which every instantaneous rate of change is positive. That would be the idea of an increasing interval. A decreasing interval, of course, would be every IROC is negative, right? Where every single value is increasing and decreasing. Let's draw like a random cubic here. So let's go x minus 1, x plus 1, x minus 3. Okay, and you could see that, like, if we look for the maximum here between -1 and 1, there's a little maximum up there, there's a little minimum between 1 and 3, right? And there's a little max and there's a little min. So x equals x of a and x equals x of b. Just create some intervals here. So as an example, okay, so let's say, just kind of make this a little, you can see that this graph, okay, it's increasing up until this value, whatever this is, right? Looks like negative 0.015 or something like that. It's increasing up until this value. It is flat at this value. It is neither increasing nor decreasing, right? It's a maximum, a local maximum. It's not a maximum for the entire function, of course, because the function goes higher over here, but it's called a local maximum because it's sort of the highest point in this region. Now, in between the max and the min, you can see all the instantaneous rate of change would be negative, right? All of these tangents would be negative in this region, and this region is decreasing. Finally, in this third region, we would say the function is increasing again because all the tangents would be positive, all the rates of change would be positive. Yeah. Okay, so when we talk about a function is increasing or decreasing, remember we always read functions from left to right. So you can see if you read this from left to right, it's rising. From left to right, this is falling, and from left to right, this is rising again. So this function increases and then decreases and then increases again, as an example. Okay, a turning point would be a point where the function stops increasing and starts decreasing, or vice versa. So for example, right here, this is a turning point and this is a turning point, and that should make sense because the function basically turns around at either of those values. So if it changes from increasing to decreasing, then you have a local maximum. If it changes from decreasing to increasing, then you have a local minimum. This is a bit different than the term absolute maximum or absolute minimum, which would be the highest or lowest point on the graph, period. Now, notice that in my function, an absolute maximum or minimum don't exist because it goes down to negative infinity and it goes up to positive infinity. It does not have an absolute max or an absolute min. Not every function is going to have one of those. Not every function is going to have a local minimum or maximum either. It just depends on what function we're looking at. Now, another point we need to understand is the concept of end behavior. End behavior is asking you the following question. If you were to look at the function in an extremely zoomed out way, would you see it doing that, where it's as x approaches negative infinity, y goes to positive infinity, and as x approaches positive infinity, so x approaches infinity, y also approaches infinity. This one would be x approaches infinity, y approaches infinity. Sorry, x approaches negative infinity. Apologies for that one, because we're at the left side of the graph here. X approaches negative infinity. You could imagine how this might be different, right? We might have a function that, like, starts down here and ends up here, something like that, like something that does like this or something in the middle. And you would say as x approaches negative infinity, as x goes very, very, very far to the left, y goes and approaches negative infinity as well. It goes down. Here, as x approaches positive infinity, so in other words, the more we go to the right, the higher y will go, right? And that's the concept of end behavior. It's asking you the question, what does the function do as x gets larger and larger and larger? Does y get larger and larger, or does y get, more and more negative, basically? It's one of those two choices, right? Does it rise up to infinity, or does it fall down to negative infinity? And, the example that you're familiar with, which would be a parabola, either has end behavior like that, or end behavior like that. But a cubic might have end behavior like this, or might have end behavior like that. So there's 4 different combinations you can have, right? And it'll depend on what we're looking at, which one that we want to describe. Okay, so end behavior is the idea of if you were to look very far to the right or very far to the left, would the function be rising or falling at those values? Okay, so some starting points. So here we have a straight line. Describe the end behavior. As x approaches infinity, so again, the farther you go this way, y will also approach infinity, the farther you go that way. As x approaches negative infinity, y also approaches negative infinity, because the further you go to the left, the further down the function goes. It does not have any turning points, because you can see that it's always increasing. It's never decreasing. You can't have a turning point if you're always increasing, because remember, a turning point would be where your function swaps from increasing to decreasing. The increasing interval of this graph would be x is any real number, and that it's always increasing, right? The decreasing intervals would be there is no decreasing interval. That graph is always rising. Okay, it's never falling. Okay, the next one is just sort of a carbon copy. It's just with the reverse slope. As x approaches infinity, y approaches negative infinity. As x approaches negative infinity, y approaches positive infinity. Again, the further you go this way, the farther up it is. The further you go this way, the farther down it is, right? That's kind of what the idea would be there. Once again, there are no turning points. There are no increasing intervals, and the entire function is a decreasing interval. So we would just say the decreasing interval is all real numbers. It's true at all points, not just at a particular interval. Okay, now when you're looking at this one, the quadratic, okay, as x approaches infinity, so the further you go this way, y also will approach infinity. And as x approaches negative infinity, the further you go that way, the further you go up. Y also approaches positive infinity. Now it does have a turning point. The point appears to be 3, -2. That's a turning point, and we could classify it. Let's classify it as a local min and also an absolute min, because not only is it the smallest value in its neighborhood, it's also the smallest value of the entire function ever, hence the absolute min. Now, intervals. Let's talk a little bit about interval notation, because we didn't really discuss it in Unit 1. Suppose I say x, I want to say when is it increasing? I want to say it's increasing for all values bigger than 3. So I'm going to say x greater than 3. And I want to say it's decreasing when x is less than 3. Right? It would be over here, it would be decreasing. Notice at x equals 3, it is neither increasing nor decreasing, rather it is flat at this particular point, right? It is flat at the exact minimum. It would have a flat tangent at that point, okay? Okay, let's tackle the cubic. So the cubic, again, we would say as x approaches infinity, y approaches negative infinity. As x approaches negative infinity, y approaches positive infinity. And that's just, again, just looking at the way that the chart looks this way, like that way, like so. It has a local min at -4, -2. It has a local max at -1, 5, and it has no absolute min or max, because as you can see, it goes up to infinity and down to negative infinity, and therefore never sort of has a highest or lowest value. Where is it increasing? It's increasing in between x is -4 and -1. It's decreasing when x is less than -4 or when x is bigger than -1, right? So that would be, sorry, this should have a less than sign there as well. Okay, so it's increasing. Remember, it's increasing when the graph is rising from left to right. So you sort of draw it like this. It's decreasing. It's decreasing over this little piece. It's increasing over this piece in the middle. And then it's decreasing again afterward. And of course, at the exact values, it's flat and flat, right? So you can sort of break it up into 3 segments. A decreasing segment, it would decrease until -4. Then it would increase in between -4 and -1. And then it would decrease again after -1. Okay, and that would be how you would discuss that increasing and decreasing. All right. Okay, so we're going to look at some cubics, we're going to look at some quartics, and then we're going to make some conclusions. Okay, so let's get some basics down about polynomials that you already know. We're not going to spend a ton of time on this, but let's just have it down for sort of like a review sort of thing. All right, so if you have a degree 0 function, that type of function is a constant. In standard form, we would just say f of x equals c. Like, for example, f of x equals 6, right? And you know what that looks like. It would just look like this, where this would be y equals 6, right? It would just be a flat line. Minimum number of x-intercepts would be 0. Maximum number of x-intercepts would be infinity, right? If the line x equals 0 was your line that you were drawing, then it would go right on top of the x-axis, and every single point would be an x-intercept. So the maximum number of x-intercepts would be infinity. Kind of silly that would come up. Why would you want to know the x-intercept if every point is an x-intercept? But just to be technically clear, let's just be clear about what they're asking. Okay, what about degree 1? If you have a degree 1 function, you have something that's linear. The standard form would be mx plus b is normally what we would expect to see there. The minimum number of x-intercepts, there must be 1. There must be 1. You can't draw a line that has a slope that doesn't cross the x-axis. No matter what slope you draw, right? All these lines cross the x-axis sooner or later, and they all have to cross the x-axis at one point, and only one point, right? So even if you draw a line like this, it's like very flat. Eventually, of course, it reaches the x-axis, and it will only reach the x-axis one time. The maximum number of x-intercepts is also 1. So you know it has 1 and exactly 1 every time. Now the quadratic, right, which is one you've spent a lot of time on in grades 10 and 11. The quadratic is normally ax squared plus bx plus c would be the standard form. We know that it describes a parabola. We know it's possible for a parabola to have 0 roots. Suppose you had a parabola that just looked, it opened up and its vertex was above the x-axis, then it doesn't have any intercepts. But it could also have up to 2, right? For example, imagine the same parabola but opening downward, and it would connect with the x-axis in 2 places, right? So, so this is kind of like, we're looking for a pattern here. Now, we only have 3 things, and one of our things is kind of strange, right? The infinity there is kind of weird. But let's start looking for a pattern in terms of x-intercepts and in terms of how many x-intercepts you might have and how many x-intercepts you must have, right? That's what this section is all about. So we're going to begin by graphing a whole bunch of cubics. And, I think the strategy here, ideally you would draw these on your own, and then, we would look for patterns. I think that's, maybe not going to be that possible with this format. So let's we'll do them together, and then we'll talk through the patterns. So our first function that we're supposed to graph is x cubed. Notice x cubed has it looks like this. Like it looks like a parabola that opens down, and then it turns into a parabola that opens up. It's kind of like what it looks like, right? So it's like it has a flat tangent, by the way. And this is kind of unique that the tangent is flat right at that spot, but it's not a minimum or maximum, right? It's a different sort of thing that we'll learn more about later. Okay, next graph they wanted us to draw was 2x cubed take away 6x squared, so 2x cubed take away 6x squared. And that creates something like this, okay? So we want to have it bounce off of 0 and then pass through at 3, so something like that. That's also a cubic. Okay, so notice right off the bat, cubics don't have the same shape as each other in the same way that quadratics do, right? Like all parabolas kind of look the same. Cubics can look similar, but they can also look quite different from each other. Like, for example, that first one we drew has no local mins and no local maxes, whereas the one we just drew has a local max and a local min, right? Okay, the next one we're drawing is x cubed minus 5x squared plus 2x plus 3. And you can see this one, sort of similar to the other two. It kind of like goes up, has a local min, a local max, and then comes down, has a local min, and then keeps going. So, something like this. Something like that, right? So looks similar to the other one on the side, but it's not. It's like centered in a different location. The next one, x minus 1, x plus 3, x plus 1. So x minus 1, x plus 3, x plus 1. That one, it has a local max and a local min, and then keeps going. Something like that. Okay, negative x cubed is, of course, reflected. Sorry, this is difficult to draw that way. Something like that, right? No, not a great sketch, but you kind of get the idea. That's negative x cubed. Okay, then we have negative 2x cubed take away 6x squared. That would just be a reversal of this one, so it would come down, bounce off, and then do that. Sort of like this. It's not a great drawing, but you can hopefully get the idea. This one, let's just have it draw this one. Okay, so negative x cubed plus 3x squared plus 2x take away 3. Alright, so what are we looking at? So it looks like it sort of comes down, reaches a minimum around here. Something like that. Okay, and the last one there is negative x, x plus 3, and x minus 2. And this one also sort of comes down sharply. Something like that. No, sorry. Let's draw it better than that. Yeah, more or less, right? All right. So, what do we notice here? What kind of things should we see that's in common? So, from your observations, complete the table below for a cubic. So here's what we're going to do. I'm going to walk you through the cubic, and then you're going to do the quartic, okay? And you know, confirm with the person beside you or something that, or another person in the class, that what you did is right, and then you know we can always look at it together in the future. But this exercise is really best done. Like if you really want to learn this, you do it yourself, right? You don't just copy me doing it. So let's talk together about what kind of patterns you could look for here. So the first thing I'm going to say about this graph, right, is that a cubic's end behaviors are always in opposite directions. You see that? It's like negative infinity, positive infinity, negative, positive, negative, positive, negative, positive, positive, negative, positive, negative, positive, negative, positive, negative. So the end behaviors are always opposite. And that's one of the best things to notice about cubics right off the bat, right? That they have a different end behavior from, say, a quadratic. Now, it should be clear to you, if you think about this, that a function whose end behaviors are in opposite directions of one another must have an x-intercept. If your function starts up here and ends down here, and you know it's continuous, because by the way, remember we said every polynomial is continuous, right? They never have any gaps or breaks or jumps or anything like that, so polynomials are always continuous. So remember, continuous in terms of like an effective definition is just your pencil can't leave the page. So again, I would ask you, how is your function going to get from here to here without crossing the x-axis? Impossible. It might come down and bounce back up, but it's definitely going to cross the x-axis at least once. Maybe more than once, but certainly at least once. And if you look at all of our cubics over here, they all have, at the very least, one x-intercept. Right? So here, this would have one x-intercept. This one had 2. This one had 3. This one had 3. This one had 1. This one had 2. This one had 3. And this one had 3. So it seems clear that we can have 1, 2, or 3 x-intercepts. We can't have 0. That's not possible. And we can't have 4. Because again, how would you draw it to have a 4th x-intercept? Right? It would be like it goes down once, twice, 3 times. In order to have a 4th, it would have to come back up, and then its end behaviors wouldn't be right. Its end behaviors wouldn't fit with a cubic, right? So a cubic must start and end in opposite directions. If it starts at positive infinity, it ends at negative infinity, and vice versa. It must cross the x-axis at least once, but it could cross the x-axis once, twice, or 3 times. It could not cross the axis more than 3 times. That's not possible either. So let's make some notes here. The minimum number of x-intercepts is 1. The maximum number of x-intercepts is 3. Maximum number of turning points is 2. Let's count the turning points again just to confirm what I just said. This one has 0 turning points. There are no mins or maxes. This has 1, 2 turning points. This has 1, 2 turning points. This has 1, 2, 0, 2, 2, 2. So I will ask you the question. Could it possibly have only 1 turning point? Does it have to have either 0 or 2? Is it possible to have only 1? I'd want an answer to that question when we get a chance. I'll give you something to think about. Could a cubic have one turning point? The number of turning points, let's specify, let's clear this up actually, forget what they're saying with maximum. The number of turning points seems to be either 0 or 2. We didn't see any with only 1. And I would like to know, is that always true or potentially always true? Right? Explain to me. Is 1 possible? From your observations, describe the end behaviors for the cubic when the leading coefficient is positive or negative. All right. So let's look at our end behavior one more time. Notice this one started low and ended high. Started low, ended high. Started low, ended high. Started low, ended high. The leading coefficient, positive, 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 and remember when this one gets expanded, it'll be x cubed plus a bunch of dots that we don't need to worry about. Remember, to get the leading coefficient, you just expand the highest variable term. So x times x times x, you get x cubed. It also has a positive leading coefficient. On the other hand, negative, 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 and negative. And notice that the negative ones have the opposite end behavior. So we can now determine a lot of stuff about a cubic, what it's going to look like, right, based on certain information about it. So we could say, for example, if the leading coefficient is positive, then the end behavior must be, as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. That must be the case if the leading coefficient is positive. On the other hand, if the leading coefficient is negative, the end behavior must be as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches positive infinity. You know the end behavior of any cubic as soon as you know its leading coefficient. If its leading coefficient is positive, you know what it's going to do. If its leading coefficient is negative, you know what it's going to do. As far as describing the shape of the graph, I mean, some people say it looks a bit like a sideways S. Right? Some of them kind of look like a sideways S. I don't think it looks like anything in particular. I think it looks like two parabolas connected to each other. So like you have a parabola and then you have another parabola connected to it, or you have this half and then that half, or you have it sort of going up and then continuing to go up like that. You know, is there a good way to describe this? I don't think so. You could say it kind of looks like an S. You could say it looks like two parabolas connected together. Whatever it looks like to you, you can write in that box. I'm not that interested. Just a useful heuristic for you to remember what the graph of a cubic looks like. I guess what we could do is we could draw the three options. It could look like that, it could look like that, or it could look like that, where it doesn't even go flat. So here it goes flat, but doesn't have a turning point. Here it has two turning points, and here it doesn't even go flat. And that's also a possibility for what a cubic might look like. Okay, so let's try and draw those a little bit better. Okay, so for this one, flat, two turning points, or never flat. Okay, those are the three different ways a cubic can look. I mean, of course, they could be reflected, right? They could, if it had a leading coefficient that was negative, they would all be flipped upside down, but the shapes has to look like one of these three. Okay, and you know, my flat one really isn't that good at drawing either. It should really look. There you go. That looks better. Okay, so something like that. Those are the three different ways a cubic might look. Now a quartic, like I say, I'm going to leave this to you. Okay, so we'll end the lesson part a little earlier, so you take some time, draw all the different quartics, right? There's 7 of them, and then try and follow the same strategies that we just followed. Make some observations about its end behavior, about the number of turning points that you see, about the number of intercepts that you see, and then try and fill this out, right? And then tomorrow, or when next time we get a chance, we'll just confirm that it's right. Or you can check the answers in the notes too, is fine. But try and do it on your own. That's the way you're going to learn it best, right? Try and do it on your own. Okay, so end behaviors of a graph are determined by the degree and the leading coefficient of a polynomial. Now again, this chart you ought to be able to figure out once you go back to this chart and finish it, right, with the cubic and the quartic. So let's add a box for the cubic, because we did that one. It's wretched, sorry. Okay, so let's add a box for the cubic. Okay, so degree 3. Cubic. What is the general form of a cubic? ax cubed plus bx squared plus cx plus d. Okay, the shape that it makes, I don't know, S shape, whatever. Okay, the minimum number of x-intercepts was 1. The maximum number of x-intercepts was 3. Now, the other thing we should really do with our chart here, and let's maybe this will help make our lives easier at the end of the lesson. Let's go end behaviors. Okay, let's go end behavior. So, in a constant, I'm just going to say this doesn't apply, because the end behavior of a constant is the same value that the constant is, so we don't really care about the end behavior. For a linear function, the end behavior always go in opposite directions. What do I mean by that? If I draw a straight line, one end behavior will be positive infinity, one end behavior will be negative infinity, right? As long as the line has a slope. And recall, if the line doesn't have a slope, we're talking about a constant, so I've already covered that possibility. If I draw this line, right, you can see that the end behavior is positive infinity and negative infinity, right? And they're always opposite. So I'm going to write opposite directions under end behavior. For a parabola, right, the end behaviors are in the same direction. So for example, in a parabola, they're either positive infinity and positive infinity, or negative infinity and negative infinity. They point in the same direction. For the cubic, right, the cubic, they either go negative to positive or positive to negative. Again, like the linear, they go in opposite directions. Opposite directions. Okay, so finish the quartic. Okay, do the page with the quartics. Fill out this page to the best of your ability. Okay, go back up here and add another row for quartics, and then see if you can figure out what this is talking about. Can you tell the end behaviors based on the degree of the function and the sign of the leading coefficient? And can you notice a pattern for functions that have even degrees or odd degrees? Okay, and that's what that's going to be looking for. So the rest of the period, work on finish up that part of the lesson on your own, and then take a look at the homework there.